This is the atom, the infinitesimal building block of matter that has puzzled scientists for centuries with its enigmatic behavior and structure. Actually, this is the most famous representation of an atom, but it's not precisely how it appears in reality. The term atom originates from the ancient Greek word atomon, signifying indivisible. The story of the atom begins with ancient Greek philosophers who first proposed the idea of indivisible particles. However, in the 20th century, groundbreaking experiments shattered this notion, revealing the complex world of subatomic particles. But what exactly is an atom, and how does it shape the world around us? Let's delve into the true nature of atoms. An atom, in its most fundamental form, is the smallest unit of matter indivisible by chemical means. It stands as the fundamental cornerstone of chemistry, representing the tiniest division of matter that can be split without releasing electrically charged particles. Furthermore, it embodies the smallest form of matter, exhibiting the distinctive properties of a chemical element. Today, we know that atoms consist of three essential components. An atom consists of a central nucleus, which contains positively charged protons and electrically neutral neutrons, surrounded by a cloud of negatively charged electrons that orbit the nucleus. An atomic nucleus is formed by a specific count of protons, denoted as Z, representing the atomic number, and a specific count of neutrons, denoted as N, representing the neutron number. A proton, symbolized as P, H+, or 1H+, has a positive electric charge of +1e, which represents the elementary charge and contributes to the atom's atomic number, which determines its chemical identity. The atomic number of an element is represented by the symbol Z, as mentioned earlier. The term proton originates from the Greek word for first, and it was Ernest Rutherford in 1920 who assigned this name to the nucleus of hydrogen, which is indeed known as the lightest nucleus. In the nucleus of every atom, you'll find one or more protons responsible for generating the attractive electrostatic force that holds the atomic electrons in orbit. Neutrons, if any are present, contribute to the overall mass of the nucleus and help stabilize the nucleus. But they do not influence the atom's charge and do not significantly affect the atom's chemical properties. The number of neutrons in an atom's nucleus can vary, creating different isotopes of the same element. Neutrons are abundantly generated during nucleus fission and fusion processes. However, they're not just passive bystanders. They play a crucial role in the creation of chemical elements in stars through a combination of fission, fusion, and neutron capture mechanisms. Protons and neutrons together make up the category of particles called nucleons. The total number of nucleons, including both protons and neutrons, in an atom's nucleus is referred to as the mass number, symbolized as A. While protons and neutrons were initially believed to be elementary particles, in the modern understanding within the standard model of particle physics, they are now recognized as composite particles consisting of three valence quarks. Specifically, protons consist of two up quarks with a charge of +2/3 e and one down quark with a charge of -1/3 e. For neutrons, this composition involves one up quark with a charge of +2/3 e and two down quarks with a charge of -1/3 e. Alongside neutrons, protons are categorized as hadrons. Electrons are negatively charged particles that orbit the nucleus in electron shells or discrete energy levels. The arrangement of electrons in an atom's electron shells determines its chemical behavior as it participates in chemical reactions and its reactivity. This electron configuration follows specific rules, including the Aufbau principle, Pauli exclusion principle, and Hund's rule. The attraction between opposite charges holds the atom together. The electrons within an atom are drawn toward the protons within the atomic nucleus due to the electromagnetic force. But what keeps the nucleus stable despite the positively charged protons trying to repel each other? It's the strong nucleus force, a powerful interaction that binds protons and neutrons toward within the nucleus, overcoming an electromagnetic repulsion. The nuclear force is typically more robust than the electromagnetic force. However, in specific situations, the repulsive electromagnetic force can outweigh the nuclear force, leading to the fragmentation of the nucleus and the creation of various elements. This phenomenon is referred to as nuclear decay. An atom is a particle which serves as the fundamental unit of chemical elements. Chemical elements are the fundamental substances that make up all matter. However, it's essential to note that only a fraction of the mass and energy in the universe is composed of chemical elements. The majority of the universe's mass and energy remains enigmatic, making up the estimated distribution of dark matter and dark energy, which continues to challenge our understanding of the cosmos. Each chemical element consists of a unique type of atom, and each atom of a specific element has a distinct number of protons in its nucleus. As an example, take the atomic number of chlorine, which is 17. This implies that every individual chlorine atom possesses 17 protons, and conversely, any atom boasting 17 protons can be identified as a chlorine atom. Sodium has 11 protons, copper has 29, and all atoms with 6 protons are carbon atoms, regardless of the number of neutrons. So elements are distinguished by their proton numbers. The number of protons in the nucleus of each atom of a specific element is referred to as the atomic number of that element. It is a fundamental property of each element and is represented by a whole number in the periodic table. The atomic number uniquely identifies an element and determines its chemical properties. There are 118 known chemical elements, with 92 occurring naturally and the remainder being synthesized in laboratories. These naturally occurring elements each possess their own distinct properties and characteristics and can combine in various ways to form the vast array of compounds and materials found in the universe. These elements are organized in the periodic table, where they are classified based on their atomic number and chemical properties, providing a structured framework for understanding and studying the diversity of matter. Atoms are incredibly minuscule, generally measuring approximately 100 picometers in diameter. Imagine this fascinating fact. A human hair spans about 1 million carbon atoms in width. This size is tinier than the shortest visible light wavelength, rendering atoms invisible through conventional microscopes. Furthermore, due to quantum effects, predicting their behavior precisely with classical physics is not feasible. The size of a whole atom depends on the specific element. The size of an atom is typically on the order of 0.1 to 0.5 nanometers in diameter. Atoms are significantly larger than their nuclei. The size comparison between the nucleus and the whole atom is mind-boggling, underscoring the remarkable void within the apparently compact realm of atoms. The nucleus, which contains protons and neutrons, is incredibly small compared to the overall size of the atom. The size of a nucleus varies, ranging from approximately 1.70 femtometers for hydrogen, which is roughly the diameter of a single proton, to about 11.7 femtometers for uranium. These measurements are significantly smaller than the overall atomic size, which includes both the nucleus and the electron cloud, by a factor of approximately 26,634. Uranium has an atomic radius of about 156 picometers to around 60,250. Hydrogen has an atomic radius of about 52.92 picometers. In reality, the atom is mostly empty space due to the vast orbits of the electrons relative to the size of the nucleus. To put it into perspective, if we could magically magnify an atom to the size of a stadium with a nucleus located at the center, the nucleus itself would be nothing more than a tiny grain of sand at the center of the stadium. The rest of the stadium, which is mostly empty space, represents the electron cloud, where electrons are found orbiting the nucleus. This stark size comparison reveals the astonishing emptiness within the seemingly solid world of matter, a reminder of the enigmatic nature of the atomic realm. Even the hardest substance known to date, a diamond, is significantly over 99.9% empty space at the atomic scale. Despite the nucleus being exceedingly tiny in comparison to the entire atom, more than 99.94% of the atom's total mass is concentrated within its nucleus, with protons and neutrons making up the majority, while electrons contribute very little. This dynamic interplay of charged particles gives atoms their distinctive properties and characteristics and allows them to interact, forming molecules and giving rise to the diverse world of chemistry and the materials that surround us. Protons have a size on the order of femtometers. Because protons are not fundamental particles, they possess a measurable size, known as the root mean square charge radius, which is approximately 0.84 to 0.87 femtometers. In 2019, two independent studies, utilizing different techniques, determined this radius to be 0.833 femtometers with an uncertainty of plus or minus 0.010 femtometers. The mass of a neutron is significantly greater than that of a proton. The mean square radius of a neutron is approximately 0.8 femtometers. Electrons are much smaller than protons and have a size that cannot be precisely measured due to their wave-like behavior, but their electron cloud extends over the entire atom. The mass of an electron is roughly 1,836 times smaller than the mass of a proton, or about 0.000545 times the mass of a proton. The electron is considered to be dimensionless, so electrons have no size in the classical sense. As we've previously discussed in my video, the standard model of particle physics, quarks are the fundamental constituents of matter, elementary particles that make up protons, neutrons, and other hadrons. The mass of a proton is approximately 80 to 100 times larger than the combined rest masses of its three constituent quarks. The mass of quarks contributes only a small fraction, approximately 100% to the overall mass of a hadron. The bulk of a hadron's mass arises from the binding energy of quantum chronodynamics, encompassing the kinetic energy of quarks and the energy of gluon fields that hold the quarks together. Quarks are currently considered point-like particles as well, with no known substructure and no size in the classical sense. Their size is not measurable in the same way as composite particles. The periodic table is like a map guiding us through the incredible diversity of atoms. It's a map to understanding the unique characteristic of each element. How atomic number, mass, and electron configuration define each element's unique characteristics. At the heart of this map is the atomic number. It's like an element's address, telling us how many protons it has. This number defines an element's identity and its place to the periodic table. Mass too plays a crucial role. The total mass of an element's protons, neutrons, and electrons affects its behavior and properties. It's like the element's weight in the atomic world. Electron configuration is all about how electrons are organized within atoms. This arrangement dictates how they interact with other elements, shaping the behavior of the atomic world. Together, these factors paint a unique picture of each element. They tell us about an element's reactivity, its appearance, and even its role in our world. In one of my upcoming videos, we'll delve even deeper into the fascinating world of the periodic table and explore the elements in more detail. Atoms extend beyond theoretical concepts. They possess tangible, real-world implications. Their significance spans across diverse fields, from enhancing food safety and quality in the food industry to serving as a cornerstone in environmental science for monitoring pollution levels. These minute entities significantly impact our daily lives. We'll delve deeper into these practical applications in one of the upcoming videos. What lies ahead in the realm of atoms and their incredible potential? Scientists are harnessing atoms for cutting-edge technologies like quantum computing and nanotechnology. We'll delve deeper into the future of atomic science and explore how atomic research is aiding us in the exploration of the cosmos in one of the upcoming videos. Stay tuned for this exciting journey into the future of atoms. Overall, atoms are the fundamental building blocks of matter, and their properties and interactions play a crucial role in understanding the physical and chemical behavior of the universe. We've explored the structure of atoms, their significance, and their profound impact on our world. As we conclude our journey, I hope you've gained a deeper appreciation for the remarkable world of atoms. These tiny entities are truly amazing, and they're still full of mysteries that we're only beginning to understand. Their secrets continue to inspire scientific exploration. Thank you for joining me on this journey into the heart of matter. Be sure to check out my related videos for more fascinating insights into the world of science. If you found this video interesting, don't forget to like, subscribe, and share my channel for more captivating scientific explorations. In my next video, we will continue to explore more topics related to atoms with even more interesting details. Until then, keep exploring the wonders of science.